A separate video recording has demonstrated the basic idea and processing behind the Cerno-MS calibration and formula determination technology in detail. With the release of MassWorks version 4.0, this process has been made even easier and simpler, especially for Agilent GC MSD users, through a uniquely available AutoCal feature, which we will demonstrate here, along with added features such as NIST Mass Spectral Library Search. Agilent GC MSD has the capability to program PFTBA calibration gas as part of a GC run. This conveniently enables a fresh, accurate mass calibration to be built for each and every GC run, even though the GC MSD system has been shown to be stable for at least 1 to 3 weeks at a time, provided that the MSD uses the same tune file. Instead of performing the manual calibration, including the following steps: 1. Retention time window selection for spectral averaging. 2. Standard ion selection. 3. Calibration. 4. Reviewing and checking. 5. Saving the calibration file. And 6. Applying the calibration file. The AutoCal feature would automatically detect and process the PFTBA calibration data inside any GC MSD run, and then go through all the above steps 1 through 6 automatically, so that only one single step operation is necessary to obtain the accurate mass and high spectral accuracy. There are 2 ways for AutoCal to work. 1. Inside MassWorks software, under Analysis mode. Upon opening a GC MSD data file, the AutoCal would detect the presence of PFTBA and start the whole calibration process. Within a few seconds, the calibration file would be generated, saved, and applied to the GC MS run. One could then go straight ahead and perform the accurate mass analysis for any ions within the run. Two, inside ChemStation Data Analysis software, a new menu item called MassWorks would be added and available to allow MassWorks to be launched directly from within ChemStation software, with the currently loaded ChemStation data opened inside MassWorks. The AutoCal would immediately proceed to completion, with the calibration file created, saved, and applied to the data, with accurate masses displayed in the mass spectral window right away. For this unknown peak at 8.7 minutes, we would right-click to select Mark an RT window, and then left-click once on the left and once on the right to indicate the RT window range to average the mass spectral data for better signal-to-noise. We could then adjust the bounds of the RT window. The graph below here shows the averaged mass spectral data with the PFTBA calibration automatically generated and applied. As we can see, there are quite a few EI fragments created and measured here. The largest ion, possibly the molecular ion, is located at 240 Daltons. Its accurate mass is now displayed to the 4th decimal place, and is typically accurate to the 3rd decimal place as 240.0110. While it is nice to determine the accurate mass location for this unknown ion, using just a conventional GC-MS system, it would be even better if we could get its formula, or elemental composition, to see how many carbon, hydrogen, nitrogen, oxygen, etc. may be involved. This is a capability typically reserved for the more expensive, higher resolution MS systems, but is now available to single or triple quad MS users, thanks to the special PFTBA calibration and the high mass spectral accuracy achievable on these systems. We can start the formula determination process by right-clicking on the accurate mass label here to bring up a Eclipse Search dialog page. The accurate mass has been copied over here, and you typically search within plus or minus 15 or 20 millidaltons mass tolerance window, reflecting roughly 3 times the expected standard mass error of about 5 millidaltons. Since this is a molecular ion under EI mode, the electron state may be set to odd here. Otherwise, it may be even for electrospray, or both if it may be a radical ion fragment. We can enter any possible elements here from the periodic table for consideration. For organic compounds, we typically start with C, H, N, and O. Notice that all of these elements can start from 0 to allow for the possibility that some of these elements may be missing from the actual formula. The maximum number for each element is automatically filled in by the software, which is typically unnecessarily large. One can either turn on the empirical rules to automatically limit the search to common compounds, or to overwrite these elemental limits. The elemental composition search results would then be more limited to what one may expect based on possible chemistry. We leave the double-bound equivalent range wide open here, since we are treating this ion as a total unknown, with unknown numbers of rings and/or double or triple bonds. The profile mass range here specifies the mass spectral range within which the spectral accuracy match would be performed. We will come back to this point later. We can click Save as My Defaults button here, so that the next time we would simply recall this set of parameters. If I click the Search button, MassWorks will now make a list of all possible formulas whose exact monoisotope masses fall within the 15 or 20 millidalton mass tolerance window of the measured accurate mass satisfying the specified conditions on this sheet. There turns out to be 19 formula candidates. The question now is, would one of these 19 formulas be the correct formula, and how would we decide? This is where the concept of spectral accuracy comes into play. For each of these 19 candidate formulas, a theoretical mass spectrum could be accurately computed, conforming to the same peak shape function that the measured mass spectrum has been calibrated into. Each theoretical mass spectrum would then be compared to and overlaid with the calibrated mass spectrum of the unknown to arrive at a spectral accuracy metric, reflecting how closely matched they are to the unknown mass spectrum within the given profile mass range. MassWorks sorts these formula candidates based on their spectral accuracy, from high to low. For example, the 19th candidate formula is C20, a legitimate formula based on accurate mass. When I click this particular row, we see a large spectral error on A+1 and A+2, and know immediately this is not the right formula. In fact, spectral accuracy is only about 84%, or there is about 16% spectral error. Going up the list, we see better and better spectral match, and higher spectral accuracy. The correct formula should provide a spectral match with nearly 100% spectral accuracy, subject only to a small random noise. Unfortunately,
even the top hit, C6H8O10, would only provide about 93% spectral accuracy, with about 7% spectral error. If we examine the mass spectral fit here in this window, we see immediately a significant lack of spectral fit on A+2, indicating the possible presence of one or more sulfur elements. Right-clicking again on the accurate mass label, we can bring up the CLIPS search dialog page again. Since we saved our previous search parameters, all we need to do here is recall these parameters by clicking Reset to My Defaults. Add the possibility of a sulfur element to the list. Click Save as My Defaults, and perform the search again. We now see that the lack of fit on A+2 has been improved, with spectral accuracy now at about 96%. But more sulfur may be needed. Going back to the CLIPS search dialog page, we can select Reset to My Defaults, and then increase the sulfur upper bound to allow a maximum of 4 sulfurs. Saving these new defaults and performing a new search, we now see a 99% spectral accuracy at the top of a list of 63 possible hits. The top hit, C4H8N4O4S2+, contains 2 sulfurs and was later confirmed to be the correct elemental composition. In case you are wondering what other high spectral accuracy hits look like, we can select the second hit and see similar spectral accuracy fit with some minor error on A+1. For the third and fourth hits, however, the A+1 errors become quite significant relative to noise, such that we know the carbon numbers would not be correct. It is interesting to point out here that, had we used a high-resolution accurate mass instrument for this unknown ID and sorted the formulas based on mass accuracy alone, which we can do by clicking the header here, there would have been 12 hits within the plus or minus 10 ppm mass tolerance window, and none of them would have resulted in the correct formula due to the lack of spectral accuracy. This shows how much more important spectral accuracy is compared to mass accuracy. Similar to the molecular ion, one can also analyze an EI fragment ion for its elemental composition. For example, for this major fragment at 212 Daltons, we would right-click the accurate mass label here to bring up the CLIPS search dialog again, and recall previously used parameters. By selecting Reset to My Defaults. We would only need to change the electron state from odd to both, since this is a fragment ion. Performing the search again, the results indicate possible elemental compositions for fragment elucidation. Another interesting feature in MassWorks CLIPS is the capability to analyze mutually overlapping ion signals, such as the 92 Dalton and 94 Dalton fragment ions here. We again click to open the CLIPS dialog and recall previously saved default settings. Under the ion series section here, we would enter the possibility that the 92 Dalton ion is a -H2 version of the 94 Dalton fragment, and extending the profile mass range from -1 to -2.5, so as to include the A and A+1 of the 92 Dalton ion into the spectral accuracy calculation. Performing the CLIPS search now reveals the likely elemental composition for the 94 Dalton ion and its -H2 version, along with their relative concentrations of 18% versus 82%. This is very useful for at least the following two applications. 1. EI analysis of molecular ions, particularly straight-chain hydrocarbons, which may also lose a hydrogen during the EI process. And 2. Accurate relative quantitation of native and isotope-labeled ion mixtures, such as through deuterium labeling or radiocarbon labeling experiments. We would now like to show you a few other practical and useful features. Even though the AutoCal performs the calibration automatically in the background upon opening the file, we can still open the AutoCal calibration file afterwards, under calibration mode, inside MassWorks, to step through and review the entire calibration process. For either documentation or diagnostics purposes, such as examining the mass recovery as indicated by delta M and the spectral accuracy for all calibration ions. Under analysis mode, you can easily turn on the raw mass spectral data and compare it to the calibrated version by going to the Graph Settings utility window and clicking both under Show Spectra. You can also display more traditional centroid data by switching from the default profile mode to centroid mode for the calibrated data. At this point, you can move to the next utility window and left-click to select the centroid data trace, and then right-click to copy as MSP. This will put the accurate mass centroid data into the computer clipboard for NIST library search. Inside NIST MS Search, move the mouse over to the upper left graph and right-click to select Insert Clipboard Spectra, and send the MassWorks centroid data for NIST MS library search. Judging by the very low match scores, this particular compound does not seem to be in the NIST library, indicating the unique capability of MassWorks software for true unknown identification. Finally, you can look up the electronic version of the help file available inside MassWorks for a more detailed operating instructions and other features. Under Contents, you can go through the Quick Start tutorial. Under Resources, you can read about the recommended first experiment and the quick guide to keyboard and mouse navigation. You can also search for background correction on how to mark background regions in chromatogram for background subtraction. You can also go to Contacting Customer Support under Contents for information on how to contact Cerno Bioscience for email and phone support. This concludes the MassWorks with AutoCal software demo, and I hope you have seen it working, simply and easily, on an otherwise conventional quadrupole MS system, for accurate mass formula determination of either the molecular or fragment ions, even in the presence of mass spectral overlaps, such as those between the M and M-H2 ions, where Cerno technology enables accurate relative quantitation of mutually overlapping and hard to separate ion species. Thank you.